Hello everybody, thank you for choosing this presentation. My name is Michal Šujan, I am from Comenius University, Bratislava, Slovakia. In the next few minutes I will focus on how differential subsidence affects river network orientation and alluvial architecture. Proportion of channel belts in an alluvial succession is an important feature, for example in petroleum prospection or water exploration. I will shortly introduce the issue by a review of published studies in the first part of the presentation. Then I will extend the knowledge using results from a case study in the Danube Basin. It is relatively well constrained that accommodation rate changes along a river axis affect preservation of overbank muddy deposits. Therefore, braided rivers develop in low accommodation settings, mostly because river banks are formed by cohesionless sand and gravel. Single-thread meandering river prevails in higher accommodation settings due to the preservation of floodplain muds and confinement of a channel between more stable banks. The situation was described as much more complex in the case of differential subsidence perpendicular to an axis of a river. Several factors control the resulting position of a channel, including topographic gradient, substrate erodibility, erosion rate, and prevailing grain size of transported sediment. The early experimental works on alluvial architecture grouped in the so-called lab models suggested that channels are attracted to the point of maximum subsidence in a basin, as you can see on the left part of the figure. More recently was shown that the essential is whether the differential subsidence produces topographic gradient and if this is compensated by a sediment supply. It might potentially result in a dominant presence of channel belts on the basin margin, as you can see on the right side of the figure. The number of studies focused on effects of differential subsidence on alluvial architecture perpendicular to a river axis is relatively low. It relates to the need of a robust chronostratigraphy, which is difficult to achieve in alluvial settings. Naudor and Stano showed on a study from the Pannonian Basin that 2 times higher subsidence was not sufficient to produce topographic slope, and channels were mostly incised into the less resistant sands on a basin margin, as you can see on the figure on the right upper part of the slide. Hickson et al. Observed in a flume study that 3 times higher spatial difference in accommodation produced homogeneous proportion of channel belts on margins as well as in a basin central part. Another study of depositional record by Foix et al. Observed prevalence of channel belts on the basin margin in the case of 3 times higher accommodation rate in the central part of the basin. Our aim is to contribute to understanding of this issue by a study of post-drift alluvial succession in the Danube Basin. It was deposited between 9.5 and 6 million years in setting of temporally stable accommodation rates, as could be seen on the subsidence model on the right side of the slide. The Danube Basin is northwestern part of the Pannonian Basin, located between Western Carpathians and Eastern Alps in the Central Europe. Species analysis was applied to 11 outcrops in sandpits. 577 boreholes with depths between 200 and 300 meters were gained in archives, and their lithological logs were digitized. The boreholes are indicated as black dots on the map. Geochronology was established by dating of well cores from 3 boreholes by the method of autogenic beryllium-10 and beryllium-9 ratio. Together 23 ages were obtained from the samples. Let's move to the results. Autogenic beryllium dating allowed us to produce 3 age-depth models using Bacon ERP package. These models indicate that southwestern part did experience 4 times higher accommodation rate, reaching 200 meters per million year, comparing to the northwestern part of the area reaching only 50 meters per million year. Southwestern part of the area is represented by section 1 and northeastern part is represented by section 4. Borehole profiles revealed that southwestern part of the area exhibit increased proportion of channel belts reaching 10 to 40%, comparing to only 0 to 15% in the northeastern part. The area with a high proportion of channel belts contain mostly well-drained floodplain, while low proportion of channel belts is bounded to poorly drained floodplain facies. The same prevalence of channel belts on the southwestern part of the area could be seen on the Neto-Gross map of sandy units. However, the thickness of individual channel belt is very similar in both areas as could be seen on the graphs. The study of outcrops imply that the depth of a formative flow was more or less the same across the area, according to cross-strata thickness distribution as shown on the right figure. Follow transport direction was generally towards the south. Based on the mentioned observations, we can say that the succession was mostly formed by a single stream. All observations are summarized in this depositional model. We observed that up to 4 times higher accommodation rate attracted channel belts to the subsidence maxima, most probably by a topographic confinement. Meandering channels effectively redistributed sediment would lead to prevalence of well-drained floodplain. In contrary, absence of sediment delivery by channels to low accommodation area led to prevalence of poorly drained floodplain in this part. To conclude, it seems that 4 times higher differential subsidence might represent boundary conditions for relocation of major drainage from basin margins towards the center with maximum subsidence. However, more laboratory experiments and depositional record studies are needed to support this assumption. I invite you to read our paper for more details, and thank you very much for your attention.